All right, let's get right into it. Today, we're going to be talking about one of the most powerful and, yeah, maybe one of the most intimidating tools in all of computer science, the modal mu calculus. I know, the name sounds super complex, but it was built to solve a problem that affects all of us, every single day. And that problem really boils down to this. How do we make the software and hardware that run our entire world, everything from our phones to the power grid to self-driving cars, how do we make it all completely foolproof? How can we be absolutely 100% certain it won't fail in some catastrophic way that we never even saw coming? Well, the biggest challenge is just the sheer scale of it all. A modern system can have this mind-boggling, near infinite number of possible states and transitions. Trying to check every single one of those possibilities by hand or even with simple programs, it's completely impossible. It's kind of like trying to inspect every single grain of sand on a beach. You just can't do it. So this huge task is what the field calls formal verification. And really, it's a quest for mathematical certainty in a world full of these incredibly complex, interconnected systems. And let me tell you, the stakes could not be higher. Now, to solve a problem of this magnitude, you can't just throw another programming language at it. You need a really special kind of tool. You need a formal logic, a language designed specifically to reason about these complex systems. And that right there brings us to the hero of our story today, the modal mu calculus. So what is this thing, really? At its core, the mu calculus is a type of temporal logic. And that's just a fancy way of saying it's a language made to reason about how things change over time, like the sequence of events inside a computer program. But its real superpower, that comes from something called fixed-point operators. These things let it describe incredibly complex patterns of behavior. Okay, so let's really break that down, because this right here is the secret sauce. These fixed points are the engine that drives the whole mu calculus, and they allow it to ask questions that other logics they just can't handle. The best way to think about these operators is to imagine you're playing a game. First, you've got the least fixed point, mu. Think of it as the eventuality operator. It's the optimist. It's all about identifying the states from which you can eventually reach a good outcome, like a program finishing its job correctly. Then you have the greatest fixed point, V. This is the invariance operator. It's the cautious one. It finds all the states where you can always avoid a bad outcome, making sure the system stays safe forever and never hits a critical bug. So it's this dual power, this ability to prove that good things can happen and that bad things never will. That's what makes the mu calculus so uniquely powerful. It's not just another logic in the toolbox. In many ways, it's a kind of master logic. Now, of course, the mu calculus isn't the only tool out there. Verification experts have this whole family of specialized logics, like LTL, which looks at properties along a single path of execution, or CTL, which can reason about all the different branching futures. These are really the workhorses of the field. But here's the kicker. The mu calculus is so expressive that it can actually translate and express any property you could possibly write in those other logics. It subsumes them all. It's like a universal translator for system properties, which is exactly why it's often used as the heavy-duty back-end engine for all sorts of verification tools. But you know how it goes. Ultimate power usually comes with a catch, and the mu calculus is definitely no exception. All of that amazing expressiveness comes at a very, very high cost. And that catch is its computational complexity. The problem is what's known as XP time complete. And to put that simply, it means the time it takes to get an answer can grow exponentially with the length of the question you're asking. So think about it this way. If a formula with, say, 10 parts takes a minute to check, one with just 11 parts might take 2 minutes. One with 12 could take 4 minutes. Before you know it, the cost just explodes. It gets out of hand incredibly fast. And this complexity isn't just a flat wall you hit. It's more like a ladder. You've got this thing called the alternation hierarchy, which basically tells us that the more you switch back and forth between asking, can I eventually win and can I always avoid losing, the more powerful and way more computationally expensive your property becomes. Each level of this hierarchy is strictly more expressive than the one before it. But hey, the story doesn't just end there. With a powerful but difficult logic, computer scientists are always adapting their tools, right? And the mu calculus is no exception. It has continued to evolve to meet brand new challenges. The core ideas have been expanded to tackle all sorts of new problems. There's a probabilistic mu calculus that can reason about systems where things aren't certain, just likely. The graded version can ask questions like, are there at least 5 different ways to recover from this error? And there are even hybrid versions that can name and refer to specific states directly. It just goes to show you that this logic is a living, breathing tool, constantly being sharpened for the next big thing. Which really brings us to a final, pretty big thought. The mu calculus was designed for the systems of its time, but as we're now entering an era of massively complex AI and even quantum computers, systems whose behavior is often probabilistic and not at all intuitive, what will the next generation of these ultimate logics even need to do? What does foolproof even mean in a world like that?